A microbiologist is studying the effect of temperature on the growth of a certain type of bacteria under controlled laboratory conditions. A population of bacteria is incubated at a temperature of 30 degrees Celsius, and the size of the population measured at hourly intervals for 6 hours. So we can see time is in hours here. The logarithm of the population size appears to lie on a straight line when plotted against time, measured in hours, and the line of best fit is shown on the axis below. On the basis of the graph above, what is the size of the bacteria population after 2 hours? So after 2 hours, we can see that log to the base 10 of p is equal to 3. Just read it from the graph. And so that means that p is 10 cubed, which is 1,000. The equation of the line can be written in the form log to the base 10 of p is equal to at plus b. Use the graph to determine the values of a and b. Well, b is going to be 2 because that's the intercept here, and we want the gradient, so 2 convenient points would be here, and we can see it goes up 1 while it goes across 2, so that means that the gradient of that is half, and so we can say log to the base 10 of p is going to be 1/2 t plus 2. Another population of the same bacteria is cultured at 40 degrees. The size of the population after t hours satisfies this equation just here. Express the above equation in the form p equals a times 10 to the bt. Okay, so let's start with the log, and I'll leave out the 10 because if I just write log, that's what it means. Log p is going to be 1/3 t plus 2. Let's take 10 to the power of each side. Now that's the inverse function of log to the base 10. Therefore this side becomes p, and the other side is 10 to the 1/3 t plus 2. Now using my index laws, I know that a to the m times a to the n is a to the m plus n, and I can use it in this direction to write that as 10 to the 1/3 t times 10 squared. So that's going to be 100 times 10 to the 1/3 t. And I believe that that is in the right form, where a is equal to 100 and b is equal to 1/3. Determine the size of the population after exactly 4 hours to the nearest whole number. So that's just going to be 100 times 10 to the 4/3. And let's calculate that. So we've got 100 times 10 to the power of 4/3, and that's 2154. We're now asked to express the above equation, that will be this one here, in the form t equals c log to the base 10 of p over d. So in other words, we want to make t the subject. So rearranging, we've got 1/3 t is equal to log to the base 10 of p, take away 2. Now remember, we know that log to the base 10 of 10 is equal to 1. So 2 log to the base 10 of 10 would be equal to 2, and that is log to the base 10 of 100. So I've got 1/3 t equals log to the base 10 of p, take away log to the base 10 of 100. and therefore 1/3 t is going to be log to the base 10 of p over 100, and so finally t is going to be 3 log to the base 10 of p over 100. How many minutes does it take for the population to reach a size of 5,000? So we've got t is equal to 3 log to the base 10 of 5,000 over 100, or 3 log to the base 10 of 50. So 3 times log to the base 10 of 50 is 5.0969. Now time was in hours, so 5 times 60 is 300, and then we've got the 0.069. If we times that by 60, that's 5.81, so we'll say 6. So we'll say it's about 306 minutes. And finally, for this very long question, with reference to parts A and B, describe the effect of temperature on the population growth of this type of bacteria. I always like to draw pictures of things. So we've got two different graphs, and the orange one was the 30-degree one. The green one was the 40-degree one, because we know that the gradient of this one was 1/3 and the gradient of this one was 1/2. So the 30-degree has a greater growth rate